Welcome everybody, and my talk is about PI streams and CI interfaces. So can a deeper look at the software Cloudy help us find new phases in the CGM? So there's a lot of acronyms going on in here, but the basic idea is what we're going to do is we're going to look at the software and we're going to make some definitions, and that'll help us find things. So what we're going to be talking about is what's called the circumgalactic medium. So what this means, sort of very roughly, is the gas that's inside the dark matter halo but outside the galaxy. So, we know the current paradigm of galaxy evolution is that galaxies live at the center of these roughly spherical dark matter halos, which have a characteristic size within which they're gravitationally bound, which is called our vir, or the virial radius, and the galaxy is about 1/10 that size. So it's much bigger than the galaxy's extent in terms of stars, but it has a lot of dark matter and other gas in it. And since the dark matter is dark, it's very hard to actually detect. So what we're going to focus on instead is we're going to look at the gas, the sort of normal baryonic matter that's in there, and that'll help us kind of characterize the state of this gas in this region. It's also important for the galaxies themselves because the gas that's inside the CGM is flowing into the galaxies to fuel star formation. Obviously, you need more additional fuel to come in if you want to continue to form stars. And the galaxy will start to do things like have supernovas go off and have black hole physics and AGN go off that'll sort of start sending gas back out into the CGM. And that'll block the inflows or it'll stop star formation and do other things. So the way that we actually study this is kind of tricky though, because there's no stars, right? So if you had stars, you could just look at their, velocities and stuff. You could figure out their metallicities. But since it's not dense enough to form stars out there, what you have to do is you have to think about it in a different way. Sometimes you can use emission lines, and that's being done in the CGM of a couple very nearby galaxies. But since emission scales is n squared, it's very, very hard to see in the CGM of like further galaxies. So the way that we usually study it is with absorption spectra. So we look at a background object, and then we see that its full spectrum is missing some key wavelengths. Those missing wavelengths indicate that the light that came from the quasar, or whatever this background object is, went through a cloud that absorbed at a very characteristic frequency. So we can say, oh, this line is being subtracted at this wavelength. That means that it is H1, or that means it's oxygen 6, or whatever. But this region is so highly ionized, and it has different components of different temperatures, it can be really tricky. And the way to really get at what kind of gas you're looking at, it's hard to do that with just hydrogen, which is the most common element, so it's sort of the nicest in some ways. But if you want to look at like hot gas, hydrogen can only be ionized once. So if we want to look at gas that's really hot, we're going to want to use something a little bit more sensitive. So we usually use metals as tracer particles. So these are our kind of most standard tracers here. And we use them to trace out different gas phases. So we want to know about cold gas, we want to know cool gas, warm, hot gas. And so we're going to use really low ions to look for cooler gas and really high ions to look for hotter gas. And here's the basic picture of it. So this is from a review article in the CGM, where each of these boxes is a different ion, and this is sort of the best temperature to look for it and the best density to look for it. And so if I am looking and I see oxygen 6, I'm like, okay, it's approximately in this neighborhood. So that's the kind of gas that I'm looking at if I see it. But figuring out specifically what happens, especially when you're not directly on this line, but if you're over here or if your gas is down here, the gray points here are from a simulation, but we don't know that the simulation is super accurate as to the state of the CGM. We're going to want to be really careful about like how we get the correct fraction of a certain ion and not just look and say, oh, it's oxygen 6, it must be exactly this temperature and density, because that won't be true. So to talk about how we actually make oxygen 6, there's two basic mechanisms for doing it. The first one is called photoionization. So basically this is where you have an ion or an atom that's just floating around in space. It gets hit by an incoming photon from out in the intergalactic medium, or like just background radiation. This can also happen from local sources, but in the CGM, local sources are so far away that it doesn't really matter. We're just going to talk about background radiation from Hart and Medow 2012. And so what this means is that it depends on density. So the less dense you are, the more highly ionized you can become. And this makes sense because, as you go from right to left, you should think of it as getting more and more ions coming in per atom. Or sorry, more photons coming in per atom. So ionizing radiation is getting stronger, and the amount of atoms it can hit is going up as you have less atoms that you need to hit. Um, and the other mechanism is called collisional ionization. So this is where ions collide with each other at high speeds and they knock off an electron. This is just the definition of temperature, basically. So it depends on temperature. The hotter you are, the more often you'll have these collisions and the more ionized your equilibrium state will be. And the thing that makes this complicated and hard to deal with is that at the first approximation, either of these is fine because hotter gas is also going to be less dense, cooler gas is going to be denser. So if you have gas that's anywhere along this line, as you get to sort of hotter and lower density gas, it's becoming more photoionized and more collisionally ionized. So these two competing mechanisms work together. Basically, they're not fighting each other. And to some extent, that means you can use either one and get a reasonable understanding of the CGM. But it means that if you choose one, you might have a problem. If photoionization matters, but you choose CIE, or collisional ionization equilibrium, you're going to overestimate the temperature of gas, because it's going to be more ionized than its temperature would suggest, because photoionizing radiation. And if CI matters and you choose PIE, you're going to have kind of the opposite problem. You're going to underestimate the density, because collisional ionization is going to start you off with some raised ions, and then you're going to further ionize them with the incoming radiation. And that can have some impacts on trying to understand things like the baryon budget. So this is from work 2014, where they went and took all these different phases, and they said, okay, we have one phase traced out by the stars in the ISM. We have one phase traced out by various low ions. We have one phase traced out by this moderately high ion, oxygen 6, that we'll talk about a lot. And there's some things that are traced out by even higher ions. And this is going to be hot, warm, hot. And the problem is, if some ions are created by photoionization and some are created by collisional ionization at the same time, then you might not be sure that these states are all distinct. So for example, what we're going to find is that oxygen 6 can live inside clouds that are sort of too cool for it according to collisional ionization. And so this oxygen 6 cloud might actually correspond with this low ion cloud. And I think that was accounted for. That's kind of what these massive error bars are. So this is the minimum amount in each phase, and here's the maximum amount. But if you want to narrow that down, you're going to have to make sure that this phase has no overlap with this phase, et cetera. So we're going to dig into this a little deeper. So this is an output from Cloudy, which is software that, among other things, can calculate the ionization fractions of different ions as a function of temperature and density. And what it gives us, if we do that, this is a contour plot. So kind of like a topographical map, this is the peak, and this is a second peak. So there are two peaks in temperature density space. One of them is temperature independent and cold. The other one is density independent and hot. So that's this one. Temperature independent, so up and down has no effect, and cold, and density independent, so left and right has no effect, and hot. And we could just say, this is PI gas and this is CI gas. And that would be sort of true, but the problem is that's not super rigorous, because what happens to gas inside, regions that are neither peak? For example, that image from the last graph from the review article put oxygen 6 right here, because this is its peak temperature and its peak density, but this is actually not a peak point in 2D space, right? It's only a peak in each of the one dimensions separately. So this is, it's not clear whether you'd call this photo or collisionally ionized. And this is certainly not where all the oxygen 6 is. It's actually almost all somewhere else. So a few people have tried to do this definition in the last few years. The first one that I'm going to show is, and these are all kind of doing different things with it, so they're not getting at the same problem in the same way. But in Stern 2018, they defined it this way. They said, okay, let's not try and figure out the characteristics of all of the gas in all the 2D space. Let's just say there are two possible scenarios and see which one's better. Is this scenario, so the two scenarios, these red dotted lines, is this scenario, the high pressure scenario, more likely to give you the oxygen 6 that you see, or is this scenario, this low pressure scenario? And if the low pressure scenario is better, according to various other metrics besides oxygen 6, then you can say oxygen 6 is mostly photoionized. And if the high pressure scenario is better, then you can say it's mostly collision. So right, that's one approach, is just to split it into two things and not think about what's going on in between so much. A second approach is what Fireman 2020 did, which is where they drew in this nice vertical line, this green dotted line, and said, okay, on the right of this line, we don't have to worry about photoionization, or we don't have to worry about photoionization. Collisional ionization at equilibrium is fine for oxygen 6. And on the left side of the line, we do have to worry about it. So they basically just said it was like a complicating factor you have to think about only in some circumstances. And they noticed that when you turn on photoionization, and this is actually a crucial point, if you turn on photoionization, you'd think you'd get more high ions, right? Sort of intuitively, it makes sense. But what you find is that turning on photoionization turns your oxygen 6s into oxygen 7s, turns your oxygen 5s into oxygen 6, and depending on where you are on this graph, you may net loss oxygen 6. You may lose some of it and get less. And that's what you're seeing here is if these lines were all flat, you'd have collisional ionization, and they actually are decreasing in this region that the CGM is. That's what the red line is. And the third one I want to show is, now this is from a simulation output. So the colors are basically gas particles in a simulation. And they said, okay, let's just draw this box that goes around, this feature. And that's collisionally ionized gas. This box is photoionized. And then when you do that, in at least their simulation, you say, oh, all the oxygen 6 is from collisional ionization. And so we are not going to use quite any of those because we actually want to be especially careful around this region, because this is an output from our simulation. I'll talk about our simulation in a little bit more later, but it mostly lives right along this border region, right? So if I draw a vertical line, it's going to be really different results than if I draw a horizontal line or a diagonal line or something else. So we're just going to want to be really careful about that. Here's the definition that we started with. And this is in a paper, the paper that I was first a co-author on by Fabregat et al. 2019. And so what we noticed was that if we turn on and off photo and collisional ionization separately in cloudy, if we turn on and off photoionization, it doesn't matter for your oxygen 6 fraction above 10 to the 5.5. So it doesn't matter if it's on or off at any point up here. We also noticed that CI doesn't matter. You can turn that on and off if you're below 10 to the 5. So we got these two black horizontal lines. And what we did is we just said, okay, we know that we need to separate those two peaks in the temperature density graph. So we're just going to draw this kind of connector line in between them so that we split those things the way that we want. And so that worked okay. And we're going to get a definition that's very similar using our procedure, but we actually wanted to develop that a little bit more theoretically and make sure that it checks out like physically what's going on. And the way we're going to do that is we're going to look at how cloudy actually operates. So what cloudy does, this is kind of, we're tracing the steps of cloudy. They start with collisional ionization equilibrium. So you choose a temperature, it populates according to that temperature, and then you add photons according to the density. So how many photons you get per atom is going to equal the density, basically. And so if you're dense enough, the photons don't matter. And the way you can visualize that is with an image like this. This is your ion fraction in each of these states. So this is most of the oxygen ionization states at a specific temperature. So we took a temperature snapshot, and this is at different densities at this temperature. When you go from right to left on this graph, from here to here, you should think of that as bombarding with more and more photons per atom. So on the right, you're bombarding with 0 photons, basically. This is where all of the photons don't matter. This is all just collisional. And as you go left, you start to bombard each one, and they all start to go down eventually. So you bombard with enough photons, you're going to lose your oxygen 4 and 5, you're going to lose your oxygen 6 and 7, you're even going to start losing oxygen 8, and they're all going to turn into oxygen 9, fully ionized. So if you go low enough density, you'll become fully ionized, and all the other states will go to 0. So what we noticed is that there are only 3 possible shapes to this graph. And so the first one that we saw was, okay, let's call this shape photoionized, because what is it actually showing us? As I go from right to left, I add photoionization, I am increasing this from some negligible starting point. So it's always density dependent, and it never flattens out to a shelf like this. And if it does that, then that means that all the gas that you see that's in these states, oxygen 8 and 9, was created through photoionization at this temperature. The second kind of shape you can get is instead what we're going to call collisionally ionized. And the reason is because you start out at the high density end when photoionization is turned off, you have some amount of that ion. So that comes from collisional. And then as you go left, as you bombard with photons, you don't get more of it. You just get less. So it's only, photoionization is only killing that state. It's not making any more from like the state below it. And the third thing you could see is something that's a combination of the two. So this is what we're going to call a transition. So it starts out with some shelf of like, here's the amount of collisionally ionized gas that you have. And as you bombard with photons, first you gain some from the states below until you reach some peak, and then you start to lose them all so as you keep going further. So what you can say is that collisional ionization matters at high density, but then photoionization takes over at some point at lower density. And so if it's a transition temperature, then we can define, just to make this very like explicit and split up the whole of phase space, you can define a transition point where this is exactly, they're exactly 50-50. 50% already existed from collisional, and 50%, so that's, go up by 0.3, that's log 2 is 0.3. You go up by 0.3 and go look for where that point happens, and this is where 50%, the same amount that you started with, is created by photoionization. And as you go further, then more of it than 50% is created with photoionization. So now you've got this robust way to define Ci and Pi gas. And so these stars represent our transition points. They're at these densities, so 10 to the minus 3 and 10 to the minus 2, at this temperature for these two ions. So what we're going to do is we're going to take all of that and plot all those transition points. So these are the same ones that are denoted with stars, right? We have this green and pink stars right here. Those are plotted again here at this temperature and these densities. And this lets us split all of our ion states of oxygen, and any ion. This works, the cloudy is the same for all ions, into collisionally ionized above their line and photoionized below their line. So we always get that it's two long segments of flat lines and a slightly declining segment in between. And we went in bins of 0.1 dex. If we went finer grain, we would get more dots along this line, but it wouldn't really change the shape. And so what you see is that every ion is collisionally ionized above its line and photoionized below its line. So if you have gas up here, then all of your states are going to be created with collisional ionization except oxygen 8 and 9. If you have gas sort of down here, all of them are going to be created with photoionization except for oxygen, 2 and 3, these two. So right at any point in phase space, some of your ions are created with Ci, some are created with Pi. And just to make sure this isn't crazy, this is what it actually looks like on our phase or our contour plot here. So if I plot this green curve for oxygen 6 on top of this, we do see that it does split the peaks like we said it should. So this is the Ci peak, this is the Pi peak, but this tells us what to do with gas anywhere, including like over here or down here or like over here. Some of these places, oxygen 6 is kind of irrelevant. If you look down here, there's not much oxygen 6 at all, so it doesn't really matter. But dealing with all of this region is really important. So now we split it according to thinking about it physically rather than just looking at this plot and wanting to divide this in half. So now that we have this theoretical definition, we don't really know what it tells us, right? We still only have single sightlines when we look at data. So what we have to do, what we're going to try and do, is understand which mechanism of Pi or Ci is more important for oxygen 6 in simulations first, and then we're going to try and think about what that means for interpreting observations. So we're going to be using the VILA simulations. So this is a high-resolution adaptive mesh refinement code that has 35 high-resolution zoom-ins with realistic cosmological boundary conditions. So these have good resolution inside the galaxy, about 17 parsecs, which is pretty state-of-the-art, and they also have good resolution in the halo. Not as good, of course. It's much lower. It's about 1 kiloparsec. And that's what we're showing here is like a resolution graph. So there's a lot going on in this graph, but essentially what I want you to look at is the dashed lines, which are our sample galaxy, VILA 7. Within about 0.1 to 0.3 RVIR, we're at about 300 parsecs. Within about 0.3 to 0.6 RVIR, we're less than 1 kiloparsec in most of our mass is in cells of less than 1 kiloparsec. And out to the virial radius, 0.6 to 1 RVIR, we're still at about 2 kiloparsecs, even at best. So, or like most of our mass is in cells of 1 or 2 kiloparsecs. So the resolution's pretty good. The best that anyone's done is these really fancy specialized simulations that fixed about 500 parsec resolution in the CGM, which is about a factor of 2 better than us. But those you could only do one simulation because it was so expensive. So it's pretty good, and it'll show some of the behavior that we want to see. A couple other things to mention about the simulation is that this particular one was built before we had super good AGN implementations. So that could be a problem. There's a lot of results out there that make it suggest that we will need to talk about AGN at some point. So thinking about what effect that'll have is really important. There's a couple other papers that talk about cosmic rays and magnetic fields, which we don't include here, but they might have an effect. And the thing that will kind of get at us the most is that our simulation only runs to redshift 1. That was just economical choice because we could run way more of them. But it means that it's going to be kind of hard to compare directly to observations. We kind of have to think a little bit more heuristically about what the observations are telling us. Okay, so here's a picture of a Vela galaxy. This is going to be our sample galaxy. This is going to be our sample site-like image too. So it's always going to be this projection of we're going along the x-axis. If you look, into the screen, this is the y and z axes. And we're zoomed way out here. So this is 6 virial radius right here. So this is probably outside what you would call the zoom in region of the simulation. But the reason is just because I wanted to show the main structure that's kind of feeding this thing is you can see these 2 inflowing streams. There's one coming in from the right, there's one coming in from the bottom. They're kind of meeting up right here, and inside the virial radius, they're curling around in this clockwise manner. And so this is the gas that's sort of inflowing from the IGM and feeding the galaxy. And we can prove that in a second. But the other things to say is that this galaxy, Vela 7, it's about 10 to the 12 solar masses in total mass and about 10 to the 11 solar masses in stellar mass. So what happens when we actually look more closely? Or actually, before we get to that, sorry. We're following up with that other paper that I mentioned before, Roca-Fabrega 2019, where we found 2 things, 2 major results from that previous definition of CI and PI. Oxygen 6 is all collisionally ionized at high redshift, and it goes down with time. So that's what we're showing in this graph, with Z increasing or decreasing to 0. You have your CI fraction of all of the mass of oxygen 6. It starts out all collisional because there's no photoionizing radiation. It goes down, and then it goes to 0 for low mass galaxies, and then it starts to go back up for high mass galaxies. And what that means is that it's getting hotter. So it used to be mostly cool, and now it's mostly hot. So there's kind of different reasons for it to be photoionized at the beginning and end. We also found that oxygen 6 gets more photoionized the further you go from the galaxy. So at the center of the galaxy, or near, I guess, at 0.1 RVR, so the edge of the galaxy and this inner part of the CGM, it was mostly photoionized. And this is, changes with redshift, but it's more photoionized in the inner part, and as you go, more collisionally ionized in the inner part, and as you go out, it becomes more photoionized. But at that paper, we didn't really look at sightlines or images so much. We just did these big averages over the whole CGM, so it was kind of hard to figure out like what exactly is the structure of that. And so we're going to think about the structure a little bit more here. So this is looking at a 2D slice through the simulation. So this is 4 kind of background pieces of knowledge that we want to know about this. We have these in density and temperature and metallicity, we can see the same structure. So this is that same clockwise filament that we saw in the big zoomed out image, but in a slice. So if this is a slice, it's going to kind of go in and out of frame. So that's why it's not, perfectly filling that whole region, but it's that same object. And so we see that, okay, that inflowing stream has high density compared to this bulk, which is low density, and it's at low temperature. So this is dark as opposed to like white or orange, which is this bulk region. And the bulk region is also outflowing really fast at about 1,000 kilometers per second. So these are dense, they're cold, they are low metallicity. So if you look at this graph, you see that this is, green versus purple, which is high metallicity. But it's changing as you go towards the center. So out here, your metallicity is pretty low in the streams. In the center region, it's almost identical to the rest. So we can say, when we're going to talk a little bit more about this, this is entraining metals onto these inflowing streams, and therefore kind of negating the fact that they were low metallicity when they started. And the last thing I want to show here is a diagram that mostly is important because what it doesn't show is pressure. So these things are in perfect or nearly perfect pressure equilibrium. So you can see a little bit of structure here, but for the most part, this thing is high density and low temperature. When you multiply those together, you get that it's about the same as this low density, high temperature stuff out here. So the total pressure is really just radially symmetric. It's not super sensitive to these inflowing streams that we're talking about. So what happens when we look at oxygen 6? And kind of does what you expect, right? We drew a line that was mostly a flat temperature cutoff. So the cold stuff is photoionized and the hot stuff is collisionally ionized. I also, since I have removed all of the collisionally ionized cells, I can redo the velocity arrows, and this shows us this is moving a lot slower than the bulk regions. This is moving about 100 kilometers per second, and it's inflowing and rotating. And so we have this really high density stuff in oxygen 6, so that's green here, and this really low density collisionally ionized oxygen 6. So the photoionized is high density and small, collisional is low density and big. Which one is more important kind of depends on whether this is so much bigger than this that it offsets how much more dense this is. At least we thought that was what we were going to do. So we're going to do some quick math here. To do this math, which one is more significant? We're just going to say, okay, to get an amount of oxygen 6, you need 4 things. You need abundance of oxygen, which is constant, but you don't need to worry about that. You need the density, which we have here, metallicity, which we have here, and the fraction in oxygen 6, which we have here. So these two I showed in the last slide. This one is new. And the point is, and we need one more thing, which is the volume of the photoionized gas versus the collisionally ionized. So to do this very roughly, we have, this is about 4 orders of magnitude from the low density stuff to the high density. This is about 3 orders of magnitude from the low metallicity to high metallicity. And this is about 8 orders of magnitude from low fraction to high fraction. And this gives you about 1 extra order of magnitude because it's about 10% of the CGM. So if you just add density, metallicity, and volume together, this is the PI, the inflowing streams are higher density, lower metallicity and volume. Those basically are a wash. Like the 4 orders of magnitude here gets canceled by these 4. And so what you're left with is, okay, the inside of the streams is, 8 orders of magnitude more than the outside of the streams. So you'd expect photoionization dominates. There should be no collisional ionization contribution whatsoever, basically. And that's not what we found, which was very weird to us when we looked at this. Just doing this math very roughly right here, it makes sense that photoionization would be the only thing that matters. 1 in 10 to the 8 particles would be collisional, and that's not what we found. It's actually only about 2/3 photoionized. So that was really weird, and it agreed with what we found before in Roca Fabrica 19, but it doesn't agree with what it looks like here. So we have to think about this a little bit more closely. And when we look more closely, CI gas has really low oxygen 6 density, but not if you zoom in. If you zoom in on this, you actually see that there's these little interface layers for oxygen 6 in the CI gas that are basically comparable to PI. These are blue, these are much more significant. And so when you ask how much of the CI oxygen 6 is on that interface, it's almost all of it. It's about 90% of the mass of oxygen 6 and only about 3% of the volume. And so that means that we really have to think about not just streams versus bulk, because we already answered that. The streams are way more important than the bulk. But streams versus interface is a little bit harder because it's all concentrated right there. And in all 6 galaxies, when you do this averaging, oxygen 6 is about 2/3 photoionized by mass. It's about 10% by volume photoionized. So 90% of the CGM is this, above the line CI. But most of that is within this interface layer. So here we did this by tagging each cell. If it's self-collisional and within 2 kiloparsecs of a cell which is photoionized, then it counts as an interface layer. So we just tagged all of those and tried to do some analysis of what was in there. So what does this mean for sightlines if it's true that we have these interface layers on the outside of photoionized streams with collisional ionized gas? That means that sightlines are going to be CI dominated only if the interface is actually more important than the stream itself. And so what that looks like is that if your sightline doesn't hit a stream or its interface, you'll just get a non-detection. If it does hit a stream, you'll get photoionized if the stream is big and the interface is small and low density, and it'll be collisionally ionized if the interface is as big as the stream or has higher density. So here's what that looks like when you go ahead and do it. So this is a panel of, it's the same angle. So this is that same inflowing counterclockwise, or I keep saying counterclockwise, but clockwise filament from here. And so it is, the color is whether a sightline that goes through at that specific angle, just face on to you, is mostly going to run into photoionized gas, collisionally ionized, or equal of both. So the blue is all photoionized, the red is all collisional, the white is like 50-50, and the black is where we have sort of manually went in and crossed out all the ones where you would get a non-detection. These are less than 10 to the 13 atoms per centimeter squared. And so you get that the inner part of the halo, sightlines that go through the inner part, are going to be mostly collisionally ionized, and sightlines that go through the outer part are going to be mostly photoionized. And that's just kind of because the interface layer is staying the same thickness. Then when you're on the inner part, the interface layer is big compared to the stream. On the outer part, the interface layer is small compared to the stream. And we'll make that a little bit more rigorous later in the talk too. This is another quantitative view of the same thing. So this is the median sightline oxygen 6 column density as a function of impact parameter. And the point here is that the blue dotted line or dashed line is photoionized, the red dotted line is collisionally ionized gas, and the green is the total. So this is the oxygen 6 actual profile. And so after about 0.2 RVIR, you have sightlines are mostly dominated by photoionized gas at redshift 1. That's where we're doing this. So comparing this to COS halos with work 2013 is sort of ill-advised in some ways because COS halos data is at lower redshift than redshift 1, so we have to keep that in mind. But the main reason I want to show it here is to show that most of the detections that we get are further out than 0.2 RVIR. So if this structure is right, these outer ones are probably mostly photoionized, these inner ones are probably mostly collisionally ionized. So that can help us maybe interpret the COS halos results. So this suggests to us kind of a model that we could use for the CGM. So these inflowing cones where we have this outer bulk region, which is warm, hot, and sort of low density. We have this inflowing stream, which is cool and which is pretty high density with a certain characteristic size, A, that's decreasing as you go in, your streams are narrowing. And you have this interface on the edge, which has a certain density, which is actually the geometric mean of these two densities, as we'll talk about later, and with a certain thickness delta that is approximately constant. So, in principle, if this shape is true, this can give us all the phases of the CGM that we needed, because the inside gets cooler as we go in, the outside gets hotter as we go in, so we can get all kinds of different ionization states, which it's usually difficult to argue about different clouds that have different amounts of stuff. So to summarize so far, instead of thinking about CIE and PIE, we should be better served using a combination of both, because at a given temperature and density, some ions are going to be PI and some are going to be CI. And oxygen 6, focusing on that, is PI in inflowing streams, CI on their edges, and negligible outside. So oxygen 6 sightlines, if their detections, are going to be mostly PI if they're far from the galaxy, and CI if they're close. But there's one thing that you probably should be thinking about as I'm talking about this, which is like, are these interfaces like a real thing? Are they a real distinct state, even in the simulation, or are they just a consequence of my definition? And what I mean by that is like, if I give you a cutoff and I say above the cutoff is this, below the cutoff is this, and I give you a function that smoothly varies from one to the other, like you'll get that half of it is collisional or whatever, but it won't mean anything because it's just smoothly transitioning. So to talk about these interfaces sort of without the framework of oxygen 6 and this CI-PI cutoff, I'm going to show a couple of other ions that are not oxygen 6, although they share with it that they're all lithium-like, so they all have 3 electrons remaining, which makes them sort of easy to observe. So this is carbon 4 and neon 8, so a lower ionization energy than oxygen 6, a higher one. And if you focus on these, they show something really interesting. So I'm going to zoom in on the sort of biggest cloud that was in that slice. And this is really dramatic in neon 8, is that you actually see the interface layers show up as especially important for neon 8. The inside of the cloud is low density for neon 8 because it's too cold, basically. The outside of the cloud is sort of low density for neon 8 because it's too hot. So this is kind of the perfect temperature for just this ion to live, right? It's changing really fast over from the inside, which has one state, and the outside, which has another state. This is sort of a distinct enough state that it's changing really fast within about just a few cells, really. And on the left, we have carbon 4, which kind of shows the same thing. Obviously, carbon 4 likes the inside of the stream because it wants to be cooler, but it lives on the inside. It does not live on the outside. And you see that this blue stream is highlighted by this nice yellow outline. And that's showing you this third phase of the CGM, which is the interface. So there is a coincidence here. That coincidence was for oxygen 6. That oxygen 6 cutoff between PI and CI, which we found with totally different methods that have nothing to do with the simulation, happens to be the same as the temperature difference between the streams and the interfaces. So that might be simulation dependent. I can't tell you for sure that like with the actual state of these streams in the real universe, that they'll have oxygen 6 is cutoff is right in between those. But I think that is a possibility, and that could explain some of the things that we see. So what is this interface? So we had a few attempts to try and figure out what this was. First, we thought maybe this was a shock. So like you have these cold and relatively slow moving dense clumps that are moving, and you have these hot outflowing gas that is hitting it at much faster speed, and that kind of creates shock condition. But if that was true, we would see it in the pressure graph. We already showed a pressure graph, and it didn't appear that these interface layers were super important there. So they're not in out of pressure equilibrium, and they can't be a shock. A conductive interface might be relevant here. This is something that people are talking about, but we don't have magnetic fields, so that's certainly not how we're making it. If that changes our results, that might be important to keep in mind, but we are making this some other way. And what we settled on is I think this is a Kelvin-Helmholtz instability layer, which I'm also going to call KHI. So we have one collaborator who was a co-author on the recent paper, that Nir Mandelker, who has been looking at these Kelvin-Helmholtz instability layers from other perspectives and saying that they might be the best place to find, say, Lyman alpha blobs as an interface between cooled inflowing streams and sort of low density outflowing bulk material. So KHI basically is the situation where hotter low density gas is moving past cool clouds in pressure equilibrium. And when that happens, you get kind of turbulence forming right at the edge. So here's a picture of a Kelvin-Helmholtz instability layer from Fielding 2020, who analyzed this in a very high resolution, like idealized simulation. And the sort of rules about it are on this interface layer. So we're saying this is in pressure equilibrium. So our density and temperature on the interface have to be the geometric means of the bulk and the stream. Right, and so that when you multiply multiply density times temperature, you'll get pressure is equal in all three of the phases. And so what that'll give us is that if you have this turbulence forming at the edge of the cool cloud, which is presumed smaller than the sort of bigger and lower density cloud, one of two things can happen. Either your turbulence will disrupt the stream and kind of destroy it and make it kind of dissipate, or if your gas is also cooling at the same time, your gas can cool into the stream. So you have this gas that becomes turbulent, it becomes sort of lower, higher density and lower metallicity from the, higher density and lower temperature from the bulk material. And now it has the opportunity to cool. And if it cools fast enough, it'll just join the inflowing stream rather than sort of staying in the interface and screwing things up. And so it'll entrain more gas into the cool phase instead of damaging it. This is kind of a recycling process, because this is how that hot outflowing material with metals can join the stream and make the stream have some higher metallicity than it would have. So we estimate, since we know that this will affect how much mass is in the stream total, like mass per length, we know how much density of the stream has to be, according to this. And so we know what the volume of the stream has to be, because we have mass and density. And so if your density scales as a power law, your size of your stream should scale as that same power law -/2. And we also know that the interface thickness, when we approximate that, should be about 2 kiloparsecs. So it has kind of this smaller fractal structure, which isn't necessarily resolved, but it won't affect its bulk temperature and density. And I have one caveat here, which is that these are probably not in perfect ionization equilibrium. Right now you have gas that's being entrained in from one state to another. It's not staying long enough in the interface layer that it will necessarily be in CI equilibrium. So, keeping that in mind might change some of our results. I have a picture for that if anyone wants to see it, but it shouldn't change like the basic idea of this too much. So looking at these and trying to figure out what this tells us, so these do look like Kelvin-Helmholtz instability layers, because the geometric mean of the interface layer is very similar to the geometric mean of the bulk and the stream is very similar to the interface layer's properties as a function of radius. So here's the density, tracks very nicely. Temperature doesn't track quite so nicely. This is actually an effect that was not accounted for in Mandelker's 2020 papers, is that all of these are not temperature independent. As you go in, the cool streams get colder as they start to cool better. The hot streams get hotter, or the hot outflows get hotter as they are closer to the source. And so these are not perfectly flat lines, but mostly this looks okay. And we see that the rule that we said here about knowing the size of the streams works out okay too, because it's very hard to distinguish the streams, but the total cumulative volume of all the streams should scale as the size of a stream. You square that and you integrate it. So beta over 2 squared is beta, integrate beta plus 1. So you should see that if this scales as a negative power, then this should be that power plus 1. So we see that that's almost exactly what we're seeing here with the volume of these streams, is this has a scaling law of -1.47. and this has a scaling law, therefore, of 1 plus the negative of that, 2.4. And so this helps suggest to us a model that we can actually use to understand the CGM if we make a few simplifying approximations. So we saw before that different ionization mechanisms, we know what those look like pretty well at fixed temperature. So if we make this kind of bad approximation, which is that all these streams of bulk and the interface are all isothermal, then what that means, what that looks like really, is we're doing this. We're saying, assume these are all approximately flat. Not great, but these are all less than linear, so it's not, terrible. And if we do that, we can understand this a lot better because we know what's happening at temperature snapshots in cloudy. So if we have a temperature snapshot that looks like this, so the temperature we choose for the particular phase has this shape, then we say it's collisionally ionized. And what that really looks like is you have two pieces. You have a flat region over here, and you have a declining power law over here. And if a phase is instead has this shape for whatever ion we're thinking about, then we say it's photoionized. But that too can be written as sort of a sum of different power laws if you're allowing yourself to make some approximations. So this can break up into three. You have an increasing power law, you have a flat region, you have a decreasing power law. As long as your phase in question at this temperature doesn't overlap with this break area where this is definitely wrong, if it's down here, then this is actually an okay approximation. And then it looks like your ion fraction is a power law as a function of your density. And so, for example, looking at the stream, the ion is oxygen 6. Here's the characteristic temperature we tagged for the stream. At this temperature, here's what oxygen 6's fraction looks like. And so if you look at this and you say, okay, the blue box is the characteristic densities of the stream, this is decreasing from about 10% to about 1 part in 10 to the 6, but it doesn't have any power law break. This is kind of a nice straight line almost within this region. And so we can think about the stream as being a power law with density. The interface is mostly flat. So here's the temperature of the interface, and here's what oxygen 6 looks like at that temperature. Here's the density range that the interface is actually at. So this is nearly flat. It kind of is declining a little bit over here, but we're going to say it's approximately flat for where we are. And the bulk region is at this temperature, and here's the oxygen 6 curve. Notice it's way lower just in general. This one definitely has a break. You could say this top region is approximately flat, and this region is approximately declining. And so what this will give you, and these are all kind of not perfect approximations, but what we'd expect in the simulation at least is that we have a declining power law for the streams. We have a flat power law, or a zero power law for the interface, and we have kind of a two-part broken power law for the bulk region. And so that's exactly what we see when we actually just ask the simulation, like, what is the ionization fraction as a function of radius? So we have here a flat green line and a declining blue line, and this sort of two-part broken power law for the orange line, which is the bulk, interface, and stream. So you combine that with two other things, which is the density and metallicity. So these are also power laws, approximately. We already saw this one. This one is, an okay approximation. If you combine those together, you get this graph, which is your oxygen number density. So your oxygen number density are these nice declining power laws. You have less oxygen with radius. Multiply this by your fraction, and you get your oxygen 6 number density as a function of radius in each of these three phases. So the point here is that these are all separately power laws, or at least two of them are. The orange one has a power law break here, and so this combined with this gives you something really confusing. It goes up and down. But the blue one combines this power law plus this power law equals a flat line. And the green one combines this power law plus this power law, so it's increasing as you go in. So this actually gives us what we have, or our explanation for the crossover at 0.2 RVIR between collisional and photoionization, because that's where the streams become more dense than the interface becomes more dense than the streams. And on the other hand, another thing I want to bring your attention to is that we usually talk about photoionized gas as like we're only talking about an ionization fraction when it's more than 1 part in 1,000, right? Like 1% is kind of the characteristic cutoff of like, here's where we care about that ion. And this one declines, so you'd usually write off this part down here. And the point I want to make is that you can't quite write it off because this is increasing so much that the total scale of this stays about flat. So you do need to keep track of stuff even when only a small fraction of it is in the state you're looking at, if it's getting more dense there too. Like you're getting just more ion or more oxygen times a lower fraction gives you the same oxygen like number density of that specific ion. Okay, so I'm running pretty low on time. I might go ahead and I'll talk about this, but I might skip the last thing. So some observational results, or at least one observational result I want to talk about that this kind of can help explain is from Stern 2016. So what Stern 2016 noticed was that after observing, if you see low ions, they come with higher ions at the same time in the same lines, but the opposite was not true. Oxygen 6 could sometimes come without low ions. And the kinematics agree, so they're definitely in the same clouds when they're all present. And they tried to figure out like what could cause this structure to happen. And so what they proposed is this gray line here. So they proposed that your oxygen 6 is increasing with H1 and only up to a point, and then it flattens out. So if you don't go through an oxygen 6 cloud, then you don't get any significant oxygen 6. But once you go through an oxygen 6 cloud, you get a certain amount. And if you go through a really dense cloud, a really high density cloud with a lot of H1, you're not getting any more oxygen 6. And the reason is because in that cloud, you're getting lower ions. So you're getting low ions inside of these bigger oxygen 6 clouds. And that explains why this flattens out. And that also explains why any ion is going to flatten out. Once you go through its cloud, you could still go through denser clouds inside it, but those are going to give you just different stuff, lower things, lower ions. So we actually fill in this kind of structure that they drew with this black line kind of nicely. So we're saying, okay, if we increase H1, so that means you're going through a denser and denser part of, let's say, the stream, then we're going to increase our oxygen 6 value up to a point until we basically are going through parts where the oxygen 6 total fraction is declining. And once it's declining, then your amount of oxygen 6 is staying constant because it's getting more dense while its fraction is declining. But you're going to get higher and higher density regions, and so get some more of these low ion states as you go through. So this kind of explains something that in Stern 2016 they had to propose as kind of a phenomenological model that didn't totally check out. Okay, so I think I'm gonna wrap it up there. I've got a couple slides about future work which I can talk about, but I want to just let people ask questions. And yeah, thanks so much for having me. And this was a good time. So yeah, let's see. Does anyone have a question for me that they want to ask about this?
Yes, is it okay?
Okay, yeah, go.
Yeah, in the middle of your talk, you had this phrase, if you trust cloudy.
Mm-hmm.
Some of my questions, we've got a couple of questions are about that as somebody who's used cloudy a lot. So this is to tell you so 2 or 3 questions, and you can answer any order you want to. One is how. So we're talking about the balance between photoionization and collision ionization. So question number 1 is how sensitive is that to your choice of ionizing continuums? That's the thing to comment on. Then there's a couple of technical cloud equations where people tend to get into trouble. One is the stopping condition in cloudy. There's this command, stop, whatever it is in cloudy. So what's the stopping condition? And how does that affect things? Because quite a lot of graphs in the literature of the cloudy is nonsense with how they have the wrong stopping condition. Or also related to that, by the way, is are you doing constant density or constant pressure? The third question. Oh yeah, and the third one is the geometry of cloudy. Cloudy has a geometry where you've got a slab and the ionizing photons going in one direction, and then you get the emission lines going out on either side. But a real cloud is going to have a more complicated geometry than that. So this is my kind of 3 sort of points I'd love to hear you say something about.
Okay, so what I mostly meant with so to talk about your first thing about like trusting cloudy, the main thing I was talking about is, are we in ionization equilibrium? That's probably the most important thing for talking about the CGM is like, is ionization equilibrium right at all? Because cloudy is just generating me a table that I'm using to interpolate. And I'm not even necessarily doing that myself. I'm using a software called Trident, which was written by some of the YT people to analyze the simulation. But we're interpolating a cloudy table that was sort of pre-generated in the assumption that it's an ionization equilibrium. So whether that's true can affect kind of how much, especially collisionally ionized gas that you get, especially on this interface, that gas doesn't stay there very long. To your second point about ionizing background, that will change our results of, like, you know, we drew this line. Let me show that picture again. I think it was, sorry, here we are. So this is the picture that we ended up getting to draw when we made our definition of photo and collisional ionization and then looked at each temperature snapshot, which ions are in which kind of shape, right? Which kind of graph. And so what would happen if you change the ionizing background would be that these would kind of move up and down. And you might get that the points shift around a little bit left and right. But the basic structure, that I think high ions are always going to be photoionized for much longer than low ions, is going to remain true, if that makes sense. So these are going to move up and down, but all kind of together as a unit if you change the ionizing background for something stronger or weaker in, you know, in some very average sense. Obviously changing it in a specific sense, like changing where peaks are in the ionizing background, will have kind of really complicated effects on the one hand, but it'll, you know, all kind of wash out at the end. I don't think you'll get anything that changes the basic picture here. Your other questions are things that I, yeah, okay.
The important question is whether you have an AGN or not, because that's going to change your continuum.
Yeah, so we're not talking about local sources at all here, but it would, in principle, yeah, that AGN would cause significant changes, especially right near it, right in front of it, and, you know, even out to the CGM. I think that that would be important, for sure. Your other two questions, I'm probably not going to be as equipped to handle because I didn't run Cloudy myself, like the code of it. I got these outputs from our collaborator, Santi Roca-Fabrega, the author of the other paper, and we've analyzed these pictures a lot together, but like stopping condition, I'm not 100% sure what that is.
Okay, so that's something that you should look into, because that graph you have on the screen right now on the right, that can change quite a lot when you change the parameters of Cloudy. As a constant pressure, constant density. When does it stop? Because if obviously if it stops before your ionization changes, that's going to make a big difference.
Yeah, my guess is that we are using constant pressure because that's the kind of table we got out, is at a, or sorry, not constant pressure, constant density, because we're saying at a specific temperature, at a specific density, what is the fraction of each of these things. So we're fixing the density and temperature, and we're not fixing the pressure, for example.
So I would encourage you to explore all those things, just to make sure that graphs like the one on the right there really are meaningful and not an artifact of the parameters in Cloud.
It may become too technical, yeah, but yeah, definitely you should do. Are there any more questions?
I have a question.
Yeah, of course. Go, Robert.
Two questions. First, what's the photoionizing spectrum that you use, the ionizing spectrum in your photoionization calculations?
This is all Hart and Dow 2012 for right now. It can obviously take other things. It'd be interesting to see how it changed if we used like the new Faucher-Giguère 20, I can't remember the year, but the new paper by him.
Yeah.
But we haven't done that yet.
The second question has to do with what observational constraints one might be able to put on the ion fraction that's greater than oxygen 6. So neon 8 has a principal resonance line at 770 angstroms, and therefore at a redshift greater than, I don't know, about 0.2, 0.25, something like that, might be able to see it.
Yeah, actually, that's the thing I skipped at the very end of the talk, is that's where we want to go next, is looking at neon 8 and carbon 4, which have a little bit higher redshift data. So that's going to be a lot easier to compare with observations. In fact, here's a slide.
So are there any observations for, redshift? You were talking out to redshift 1, certainly, there you've got an HST available. Neon 8, has neon 8 ever been observed in absorption?
Yes, actually, that is the main topic of Burchett 2019. So Joe Burchett was actually a postdoc at UCSC until just very recently when he moved to New Mexico State. But his most recent paper was part of the COSBA survey, and that had a bunch of neon 8 absorption spectra and lines at redshift 1 and actually further away from galaxies too, which is also exciting. So a lot of good stuff
really
there.
important because
Yeah.
oxygen 6, to get to that, it takes about 130, 140 EV, and neon 7 to 8 is 200.
Right.
So
Right.
that would be a really interesting diagnostic for you to use.
I totally agree. So that's kind of the next thing we're doing, and we're kind of coordinating with Joe and with X Prochaska, who's one of the other main guys from UCSC on the survey, and we're going to really try and incorporate like all the ions that they get and see how they fit into this story. Is we want to basically use this model and combine it together, and just use the model itself and say, if we have a model of these inflowing streams with these thin interfaces and an outflowing bulk on the outside, can we vary the parameters of those things to give us the kinds of results we get in all of the ions we see, including oxygen 6, neon 8, and low ions and stuff that they might have in the COSMOS survey. So yeah, that's a very exciting and important thing that we're doing kind of next, but we haven't done it yet, and COSMOS not fully released yet. Like parts of it are out. Torchet 2019 is out, and this showed us like where the oxygen 6 is that they detected in Prochaska 19. That's where this image is from, but they didn't go into the details of like, all of the specifics. So we're still waiting on that, and we're talking with them about it.
So HST observations, I assume.
Yeah, this is still HST observations. It's kind of the follow-up to COS Halos, which is the big CGM survey of the last decade, I guess. There was of course a lot of CGM surveys, but it was kind of the most cited one, and this is what they're hoping to be is the follow-up to that.
Well, we just put out the CP yesterday for the next cycle, so there you go.
Everything is mapped out, Clayton. I think you have a lot of stuff to do. So we're 5 minutes ahead. That was my mistake with the recording, but the talk is recorded. So I think we can stop now and thank Clayton again for his very nice talk. And I will see all of you guys next week.
All right. Yeah, thanks so much, everybody, for coming.
Okay, thank you very much.